Hi everybody. Now we are solving a problem where we have infinitely long surface, and this surface has plus charges, okay, coming from a power supply, and the potential happens to be V0, and we would like to find what is the potential at this distance x from the surface, okay, from the surface. What we know is that the electric field at a distance x when you are near the surface is given by sigma over 2 epsilon 0. Don't forget. Okay? So if the electric field is given, then how can we find the potential using this integration? Because VB minus VA was given by minus E dot dl. Okay? E dot dl from A to B. So this was the expression that we used, okay, to solve potential difference if the electric field is known. So the electric field and known, and also this distance in terms of x, because electric field is in this direction. Also we have for dl we are using x, but for electric field in x direction we are using ex, which is given by sigma over 2 epsilon 0, and they are in the same direction. When they are in the same direction, dot product gives you just E dx. So VB minus VA will be equal to minus just E dx in our problem, from A to B. Don't forget, you have to be careful. What is A, what is B? Okay, point A is here and point B is there. Okay, because to solve potential, you have to get really points A and B very carefully. But in our case, VA is 0 and this is just V. So V minus V0 is equal to minus from 0 to any distance x times E dx, but E is just sigma over 2 epsilon 0 times dx. Okay, 2 epsilon 0 times dx. But now don't forget, this is an x integration, so that the integrand, also the limit cannot be the same, so that we just put it with prime to integrate this thing. But the advantage is that this is just a constant and it can be taken outside. Okay, so V will be equal to then V0, okay, minus sigma over 2 epsilon 0 times x. Okay, because the lower limit is 0, nothing, upper limit is x, and this is it. So we have this potential distribution. So potential distribution will reduce as x starting from B0. If we graph this, okay, as a function of x, so say this is x equals 0, the potential is V0 there, okay, and it will reduce like that, okay. So, for instance, we can ask at what distance the potential drops to 0. So, what is that? So, what is x star at which the potential is 0? Okay, so what is it? So, suppose that they ask you this kind of question. So now we can use this solution so that the potential will be 0 at any x, which is x star, so that 0 equals V0 minus sigma over 2 epsilon 0 times x star. From this expression, you can solve x star. X star will be given as, okay, V0 times 2 epsilon 0 divided by sigma. Okay, so at this distance, whatever the distance is, okay, the potential will be just 0. Okay, potential will be 0. Okay, so now don't forget, we really didn't need this thing. Okay, we just need this distance here. So at this distance, the potential will be 0, but initially be 0, and then so the potential will be reducing. The potential will be reducing from V0 to 0, and then we have this expression. Okay, so this is just a linear type of curve. So this is one question, and another one is to solve the potential distribution when there is empty disk. Okay, and the disk is, so this is another one, let's say 11. So empty disk, this is R1 and this is R2, the radii are R1 and R2, this empty disk. Again, we would like to consider the potential at any point, and we say that this is X And now, since we will name this as R inside this thing, we have to get this one, okay? So we will get the ring. In this ring, which is circular ring that goes around this hole, okay, the thickness will be dr and the radius will be just r. This is the reason that we name this as r prime. So at this distance, the potential will be given as, okay, so since there is dq inside this system, dq, dv will be equal to just k dq divided by the distance, but the distance is just r prime. So this is how we can get the potential. So, but now we have sigma surface charge distribution, which is dq divided by dA, but dA is given as 2 pi r dr. This is the dA, the area of this region. As you see, the circumference is just 2 pi r and the thickness is dr, so this is just 2 pi r dr, okay? By using this, we can write, instead of dq, we can write sigma times this expression, so that dv, or just integral will be equal to, okay, just k times, okay, integral sigma 2 pi r dr, okay, it's coming from the top, dq, which is 2 pi r dr times sigma, and then divided by distance r prime, which is r squared plus x squared. So this is an integral in terms of r, which can easily be taken because we can use now the change of variable. If we say that u is equal to x squared plus r squared, du is just 2r dr, and then when you insert here, then you end up with this expression, okay? The potential will be given as sigma over 2 epsilon 0, okay, r dr divided by r squared plus x squared square root, okay? So since this is so, we can now, instead of r dr, we can use just du over 2, and also r squared plus x squared will be given as u square root of u. So this is the integral like that, du over 2 divided by square root of u, but this is just simply u to the 1/2 divided by 1/2, u to the 1/2 divided by 1/2. This 1/2 will cancel this 1/2 there, and then square root of u, and you have to put the appropriate limits so that the potential will be given as sigma over 2 epsilon 0 in this case, okay, times square root of x squared plus r2 squared minus x squared plus r1 squared, okay, square root. So the limits were from minus r1 to r1 because this was our region, okay.